this presentation, which is about how to consider about the main and important problem of how we can link the AI algorithms to the physical embodiment of the system that we want to be governed of an autonomous intelligence system, ideally and in the future. This work is largely based on some past work for me, and also as some something towards the end of work which is still ongoing. So the main point is that we may say that with respect to the paradigm that we have in robotics, we did not do a lot of we didn't change from the past. So these are examples of automatons from the Renaissance, but they are examples for Hellenistic Greece and even from ancient China. Basically, we have a state machine that governs a mechanical structure. In the past, the state machine was implemented by gears and pulleys, that with some ingenuity were used to basically to calculate a trajectory and to react to stimuli from outside, of course, with strong limitations. Today, this is an example from actually early this century, where we implement the state machine on an array of computers. In fact, the idea of robotics is not new at all. This is Aristotle in the Republic, part of the Politics treatise, where he say that he actually points to the societal impacts of AI. So if machines could govern themselves, it says Aristotle, we would not need slaves. And modernly, we would say we should not force some of our some other person to do mundane, dirty, dangerous, or even boring jobs. What I think it's interesting in this old text from this our venerated philosopher is that if you look at the original Greek translation of this phrase, you see that he already was, from a purely conceptual point of view, well aware of the fact that you need some learning in an intelligent system. So even a physical system that performs physical tasks needed to have some capacity to predict the future and to learn from experience. And this is what actually was really written already in the, so they need, so to speak, in a sense, Aristotle was already well aware of things that we are better understanding now. So if you look at robotics, because in the end, the real target of the research of many people is to move AI from the data sets, image data sets, or even from voice recognition to the physical world. No? So we would like to have something like a programmed self-programming spider, which can be used to perform many tasks. So what robotics adds to AI is the possibility to change physically the world, so to perform physical tasks. And this has proven to be a little bit more difficult than initially expected. So you may have heard about the Moravec paradox, that things that are easy for us, like grasping an object are actually very difficult to implement with an intelligent system. However, robotics has been quite successful. We had the first wave that led to many robots in the factories, putting together mechanical engineering, computer science, control engineering, where here control engineering means basically linear control with some filtering observer. Now we are basically starting to use the possibility to interface almost everything at very low cost. I mean, 20 years ago, you could, with some pain and effort, connect your laptop to an Ethernet and then the internet by spending with a card of $200, $300 or cost. Today, you can interface everything with about 50 cents. So this opens a wealthier possibility. The other thing, and we will shortly look into this, is that machine learning, in particular, deep neural networks are made possible to recognize, recognize patterns in data with a good reliability. And then we can also write some simple plan originated from this data. However, if we look at what happened during the DARPA challenge a few years ago, we are far still, the Moravec paradox is still with us, because during the DARPA challenge, what was requested by the challenge was for this small humanoid robot to perform tasks like opening a door and entering in a room, operating a valve, a big valve, or sitting in a car and put the hands on the steering wheel. And the results were not, I mean, we're not surprised for many, but we're not very satisfactory because of this kind of, the best of those robots were able to open the door, for example, 125% of the times or less. Time passes, that was 2015, and we are here. This is the new version of the Boston Dynamics humanoid robot on the left. On the right, you have the Tesla humanoid robots. You see that a lot of progress has been done, but you should also see that to have a reasonable speed in the performing the activity, you need to increase by 20 times the speed of the video. And this is what in a famous Blade Runner movie in 1982, science fiction expected from us in 2019. So there is a big difference. This is a TED Talk in March by my colleague and friend Ken Goldberg, where basically it was, you have here a QR code so you can see the full talk, basically saying this, that we still are not able to perform this simple task. For example, opening the door and entering the room, or then of course you see many videos also on YouTube or other platforms where you see a robot making parkour or jumping from a place to another one. But this is, again, the rule is this 5%. So this requires months of work to prepare a video, and then you are able to perform 4 tasks about 5%. It's not me telling this, but actually Mark Breitbart, who is in interviews around the world, who is actually the CEO and founder of Boston Dynamics, of a company producing those nice videos. It's interesting that a couple of years ago was organized an X Prize for avatars, and the results were quite good. I mean, it was won by University of Bonn Nimbro team, by the way. But what you should notice is that we have, on the left, you see something which is similar it's a very elaborated joystick. Now, basically, you see how the intelligence is in the person. So we need while the actuation, the sensing is not so bad, how you need that person to be trained to use this avatar. You see, so if intelligence, the human intelligence running on the 10 to 14 neurons of a human brain, we can do many nice tasks with robots. But this opens actually points to the issue that concern many people in the community. So what we should do to do the next step. So the main point that I'm trying to elaborate a bit, because this is a very long, I think some years ago, there was an attempt to propose a huge European project, which is called, flagships. And unfortunately, it failed. Still, there is a strong need to try to look for different approaches, meaning that actually the new robotics project was ranked third, and in the last competition, and was actually the first of not funded flagship. But so the idea is that we need some form of to make a long story short, is some form of not only learning but also self-organization of behaviors, and that we should go towards bionics meant as really unbundling the mechanism of working of living systems, because so far the examples that we have of working physically AI are animals and plants. We have not been so far able to mimic. I mean, if you want to be optimistic, see this from a nice side, is that we see this as something that we should try. No? So, I mean, the negative side is still no good results on this side. The positive point of view, positive way to see this is that to look at this is that we think we can do by rethinking a bit, by rethinking the paradigm. I started by saying that most robots today, for example, the Avatar X Prize and the DARPA Robotics Challenges, or the robots that were discussed at TED by Ken Goldberg this year, they are the same paradigm. It's a state machine in the form of a elaborated set of many computer programs, and a mechanical system. Of course, over time, a mechanical system is much more complicated. Sometimes it has many more components. It has it's technically more elaborated, but the computers can do much more than a number of years. But that's the system. So what I have to say, we all know. So as told, I think that we should learning, already Aristotle told us that it is important. And we did some significant progress with learning. I mean, you remember 1997, with basically research, it was possible to a big computer to win against the world champion. Today, very deep, so with many very complex neural network, it is possible to win at Go. What have chess and Go in common? They are perfect information games. Of course, 35 to the 8 power is much less than 250 to the 150 power. But basically, they have something that we haven't when we act in the real world. So they have perfect information of the rule and perfect information of the state of a game. And this is never what happens in real life. So if we, I will go fast on this because I suppose that most of you know already this. So basically, the logic behind deep learning is the same of good old-fashioned neural networks. So you have you basically approximate a function. If I have time, I will also show the equation of supervised learning, no? But I think many of you know. So basically, we have this, we from layer to layer, we have a number of weights, and we train this network on labeled data. The most successful example is supervised deep learning, until we get the expected outputs. So until our system performs well on the test data and then the real world data. What was kind of surprising is that neural networks with hidden layers, with maybe if there are many different topologies. For example, you have a recurrent neural network, convolutional, so you can change the way you connect these nodes, where you basically do a sum of the input, and if you pass the threshold, you send something to the next node. This is oversimplified, but it's the good old idea of an artificial neural network. And this is just a little part of the whole world of AI, of course. However, it has deserves a lot of attention, because if you can give a simple command to an AI assistant like Alexa, or this is due to the fact that we did, and how we optimize the weights by elaborated version of gradient descent. But if you want to know more, I think this is one good reference for that. Then, while the discovery that those systems work actually came from practitioners, so I imagine. So basically, you need to think that for entities like Google, they have the possibility to train the model on literally 10 of million of hundred of million of images. So if you wanted to learn how to distinguish a cat from a dog, you have a lot of examples, and you can build networks like the one that I've shown you, much more complicated. So the real networks. But despite the fact that this comes from practitioners, now there start to be a lot of interesting mathematical research. This is a paper from 19, where if you put some assumptions, you can see that actually adding layers make your network more efficient, no? Because as you know, neural network had several waves of popularity, waves of popularity. Last was 80s, 90s of the past century. And at the end, they were abandoned because they never go above 78% of accuracy. What comes to me, at least, as a surprise is that if you have not 10, 5, 7, 8 layers, but if you have 300, and if you train of millions of examples, it converges and you have good results. And you need this kind of big data centers to train those networks. No? And we have this little problem that GPT-3 already used 175 billion parameters. And this now we are at close to the trillion, if I remember well. The cost has gone lower, but we are talking of this kind of system. So we have an AI that is the deep learning, which is what works, what allows to run large language models and things like that. And I want to enter into this, but actually it's behind Facebook and Amazon and Uber, and even now art generation is relying on these huge data servers, and it is relying on really a lot of parameters. So, and there is a kind of law of reducing return. So you add parameters, but what you get in terms of accuracy of a prediction, it becomes less. Yeah. Then, if you look at what happens in nature, we should not surprise, no? Because if you wanted to be, we are here, no? So deep learning, in particular, deep reinforcement learning can be probably put here. But all our capability to act, but also the insect's capability to act autonomously in the world is based on different scales. No? So they are nice. This is a nice example from our colleague Bongard that actually is working on this evolutionary model. And there is this thing that maybe we should look into another approach. Look, for example, looking at how the ant walk or the spider walk. So, but how we can consider, how we can quantify, because while these ideas, for example, this robot can work on a treadmill without any programming because it's the physical structure doing that. But it goes at a standard speed. So what we can do, and here I will go briefly, but it's because in the first part of the talk, with a limit of a comparatively short presentation, I have described the issue. The issue is that we should develop a kind of AI which is not for trained on huge data sets, but is trained while interacting in the world. When we interact with the world, an important aspect is the embodiment. So the fact that, for example, when we walk, we exploit, we have a kind of controlled fall, and we exploit the dynamics of an inverted pendulum, to simplify. But how I can use this information at design time, so of the control systems and the robots. There are various ways, and this would be another talk. However, for example, you can there are ways to insert. There is an area of research, a new area of research, which is physical informed neural networks of physically aware, physics-aware neural networks, where you somehow force the physics in the system. What is not well linked is how to give a quantitative representation of the capability of the body dynamics to process information. So what's the trade-off? So if you want to be emphatic, you could say the brain, this is somehow the core issue that we should try to unbundle, which is the mind-body nexus. So how in living systems that are the only working examples that we have of autonomous intelligent systems, this happens. So there is this work from Longarella and Sporns, where they trained, it was 2006, what now we would call a shallow or not a deep neural net. Actually, we are trying to do this with more modern algorithms. They saw that there was a peak in the learning of various kind of robots. For example, this humanoid, simple humanoid manipulating, when the transfer information, the predicted information was maximized. So this tells us something, no? Because the idea was to build a lightweight, let's call them deep, so in the first stage, deep learning networks that actually inherently consider the physics. So they use the physics to do things. And this can be done. And here we enter in the, if you want, in the part of a talk which is more strictly related to a specific approach to this, which is our approach, and is to rely on this, I would say, not very popular, not, to my surprise, the Shannon entropy and the related metrics have been used, applied to problem of control only quite recently, I mean 2004, and they are still not extremely popular. However, they allow to link together with Kolmogorov complexity to the state, phase state volume of a system. So this is a relation that was discovered several years ago. I think there are more approaches that can be used, but they all should look at the, for example, this is the snakebot by Tanev that is actually is an experiment that we are really trying to redo with modern learning systems and by exploiting this kind of concept. Where basically it was a toy problem, but Tanev was and friends were able to show that if you model a snake as a chain of balls loosely coupled one with the other, and you program a very high-level controller. Also, Tanev had to use the what we now call swallow neural networks, artificial neural network, where you basically have a few hidden layers instead of 100, and instead of getting hundreds of data in input. What was nice is that this simulated a snake with this very simple model, so a chain of balls loosely coupled with each other. If you force the learning to learn how to maximize the predictive information between current values on the sensor, current state of actuator, and predicted input from the sensor, so you obtain very natural behaviors. So this is interesting. Then, like I didn't have that, so maybe not necessarily we have to stay in the Cartesian space, but the question is, I didn't spend many words on the passive work. Passive workers are kind of application of an inverted pendulum that are used to show that basically an inverted pendulum can go down a slope with no programming and consuming very little energy. There are examples like the corner ranger, where you can put a very simple controller and you add a battery, and you can work for 60 kilometers with a battery. That is with other kind of designs not matchable. Problem of these systems is that they have they cannot change speed. So what's the reason why? Because you may ask yourself, so why we have this simulated snake, and we have this passive worker since now 20 years, and most robots, for example, 10 years after the snake bot, there was the DARPA challenge, and no humanoid was using those approaches. No humanoid was using passivity, if not for working. Sometimes they moved some weight to improve a bit the movement, but essentially they were fully actuated. So why? Because it's difficult. So the point is that we still need to work to develop model, and this is an attempt to develop those model where I'm afraid it would take too much time, but I will leave you. You have references, and you have. But basically, it is possible to, if you work out the relations that for a control system link the mutual information between the current state and future state, and the controller states, you can actually link the physics to. Of course, you need to do some work. Now, this, for example, I just focus on the first of these equations, but is actually the most important. Actually, here you can, a way to interpret this equation is that if you have dynamics that somehow reduces your space, the volume of your phase space when you have the controller with respect to what happens when you go in feed forward, you actually need a smaller controller. Then we know that you cannot calculate the Kolmogorov complexity, but you can bound it. And it is exactly what we do here. then I don't pretend that this is, I don't think that it is the only way to do that, but this shows that you can do that. So it's possible to see what's the balance between the, so you may have a budget, no? So because between how big is your control program and how how much you can shape the physics of your system. Because then, if you look at a robot, a robot arm, you have a series of rigid limbs connected by simple joints that are expressed by an angle, no? An angle which is the internal, is for joint coordinates, no? The internal coordinates. But if you look at this elbow or at this no, or here to the connection of the arm to the body, these are very complex and changing surfaces. So you haven't a joint, so you haven't a variable in the elbow. You have a number of intersecting faces, and you have muscles. This means that the form of a joint, not only the force that you have in the muscles of the arm, can be changing online. And this is done in some way in our brain. So how we can replicate this? We need to have ways to understand when it is, so the purpose of this equation is to see when it makes sense to change the shape here, you know, or the elbow to simplify the control, because also the computation possibility of a learning system are limited. And one big problem with when you apply deep learning system to robotics or even to computational biology is that you never have millions or tens of millions of records of data to learn from. And when you are in a robot, you also need you have a real time. This means that you cannot calculate forever. You need to learn on it. So this is I would just, yeah, there are many we could discuss for a lot of time. But the essence is I have a way to link to the I don't want to go. I think that someone could actually be surprised by this passage. But if you look at more modern, so for example, if you look at these two references that I put here, you see that it's perfectly legitimate. And I was saying about just a minute. This is actually the equation that you have here is what you really calculate. So you basically change the parameters here until this function predicts the output of an unknown model that it is in the world. So I will skip many of this.
Professor, could you...
Because I think this is actually taken from the colleagues. This is, we are here, no? So we are very good in playing Go, playing chess, playing checkers. We are better than before in natural language processing. But then we have application of deep reinforcement learning to fixed structure. The biological world is here. So is in changing structure when structure change with algorithms. We may have another side. I focus a little bit more on deep learning because it is very popular at the moment. It's possible that we need some similar progress in evolutionary algorithms, but really I think this is the open. It's if you look okay, quick example of what we are doing in our lab. So we are basically trying with a bottom-up approach to uncover these things. We are also working on, now this is someone who makes my case, which is Pedro Domingos, to say that basically there is some barrier to and I think are barriers like that I have shown now. And there are methods, there is learning of manifolds, there is information-driven self-organization. You see that at NIPS and IPS, people starting, for example, learning when you are constrained to some kind of group of motion, which is always happening in robotics. So to conclude, we really, this is the real issue in physical AI. I think we have done some progress. I think we really have, there is a lot of work for people wishing to, I think what we really miss are mathematical models. I've shown you really briefly
Professor
the
Fabio,
path that
please.
we are following, but I really think it's an area where there is really a lot of work to be done. And I mean, I like the picture, you know, because actually this eagle is a real picture, taken from a real fact. Is actually much better than a drone. Drones are very popular in these days, also for bad reasons. But so this is it's also a very practical issue. So it's, I think, a very deep theoretical question, because in the end, we want to connect complex systems science to deep learning and to information theory. But we are motivated to do that because this is not understanding well this kind of called dynamics. It is what probably, according to many, is preventing us to build drones that are more likely to the whole of a science fiction movie or to the real eagle. And the benefits that we would get from that are tremendous. And I don't think we are so far away from solving that. I don't want to say how many years, but I think this is what we should try to do to have physical AI, which is not. So it's next step of AI.
Professor Fabio, Fabio, please. Professor Bonsignorio,
thank you.
Thank you. Thank you. Conclude. So thank you for your talk. Now we have a question time and discussion time. So do we have a question towards given talk? Yeah, go ahead.
I would just have a brief comment as an Spaniard, because at the beginning you have mentioned the work from Brunello Torriano, and there is a lovely picture of Charles I or V, depending how you consider, and Brunello Torriano in the Juste Foundation. So it's really an interesting topic. And my question about this is, we have seen that this third wave, we can have.
Sorry?
Could you hear me now?
Yes, can you repeat the question?
Absolutely. So first I have a brief comment and then a question. First of all, as an Spaniard, I really enjoyed the introduction from Giuliano Torriano.
Yes.
Charles III or Charles I. And just to mention that there is a picture in Juste Foundation about the exact moment in which he is showing some of the clockwork works from Gutenberg. And the second part, in the case of this third wave, how can we solve the problem of opaqueness in the sense of these deep learning are really black boxes when they go really a lot of layers to the deep learning? How can we understand this thing? Because, okay, we can solve the problem for a single configuration, opening doors or trying to run as fast as possible directly, but how can we understand which is the process behind it, then we can replicate? Because if not, we need to train this model for each of the actions that we wanted to fulfill.
This is a very good question. There are actually recently, I mean, latest 5 years or so, there is a lot of work, for example, about, I quote actually very quickly, I passed slides about information geometry or geometrical approach to deep learning. That I think are shedding some light. So maybe I can also share with you some, if you are interested, some references. I think that you point to the issue, because how I can, because we have two extreme approaches to, for example, controlling robots. Let's say control. We want something more. We want autonomous behavior. Let's think we are just to control. You have model predictive control, where you know the underlying physical chemistry or whatever that regulate your process. And you have fully data-driven approaches like those brute force approach, because the deep learning on a Google server farm is brute force. No? So I have a lot of parameters and I run and run again until I surprise a bit to the fact that you converge, but most of the times they converge. So between these two extremes, I think that there is a third way, which is what I quoted again quickly, which is physics aware or physically informed neural networks, where you know the model that you can maybe represent in terms of symmetries of behavior, and you can use it to design the deep network. Then it's not really you can understand which part of a network is contributing to an output, doing something like a sensitivity analysis of an identification. Because in the end, deep neural networks do a very complex kind of identification of the system dynamics. No? I'm sure it is not. I think that it could help to add this kind of relations or other similar that I've shown you before. But I also think that we should add some evolutionary argument in the sense of doing some trial and error, no? Because in the end, the deep learning, mainstream at least, deep learning identify a function and does some prediction on the basis of the identifier. So I think you pointed to the real, I think that exploitation of manifolds in learning, it's a first step. And then we have other problems, but also the problem that, again, I didn't went into, which is symbol grounding. No? Because if my system have to learn a representation of a word that is good for that system, not me, designer, injecting my knowledge of a word. This requires something more, I think. I think the things are that we can, early things are equation like those that we have shown at the end. More short-term manifolds, so exploit the so represent in terms of geometry the physics of the system that you are studying. And I think we also need some evolutionary mechanism really to introduce also to create the symbols, no? But it's a very long discussion, this one.
Thank you very much.
Okay,
Thank you.
Question?